Okay, thanks a lot. Thank you for the invitation. So I want to talk about confidence or uncertainty estimates for neural networks. This is joint work with a postdoc of mine, Tiago Salvador, and with an undergrad, Alex Iannantuono, who's now a master's student at UBC. So when a neural network makes a classification, we want to estimate the uncertainty. In other words, what is the estimated probability that the classification is correct? And for deep neural networks, this area is evolving very quickly. I can't say I'm an expert in the field, but I've contributed. And so what I'd like to do is tell you a little bit about what I've learned working on these two projects in the last little while. And then after this topic, I'll move on to other ones. So what you see here is an image of object detection, YOLO, with the probability estimates assigned. And the question really is, are these probability estimates good estimates? So I found when I first got into this area, I found it very confusing, and I don't think I'm the only one. So I'm going to sort of tell a story, and hopefully it makes it a little more interesting. One thing in practice that people do, and you can see here some Reddit questions about this, is that you just take the outputs of the vector of probabilities from the neural network. They come from softmax, and you use these values as surrogates for your class probabilities. Now, when I first saw this, I thought this doesn't make any sense at all, okay? Because you could just multiply the last layer by 10 and it would change all the probabilities. So why would this be at all correct? But first off, why do people even think this way? Why would you think to use this? Well, for traditional machine learning models, some of them are trained to output class probabilities. So it makes perfect sense to do that. For example, to take something very simple, spam detection, you would use conditional probabilities based on certain words appearing, and your output is a probability. But this is just definitely not the case for neural networks. Now, there was some early theory, which is using dropout by Gal and Garamani, and they've been quite involved in uncertainty in autonomous vehicles as well. The idea behind dropout is really simple. You just wiggle the parameters of your network, do inference a few times, and then average these p-values over multiple inferences. And this works better if you tune it correctly. They gave a Bayesian interpretation. I didn't understand it. I think some other people might have been confused too. And it was later sort of retracted, but the idea was that you could somehow estimate the known unknowns, to speak sort of philosophically, but not the unknown unknowns. Okay, and so you see a more recent publication from this group, from Gall's group, on uncertainty quantification with guarantees in autonomous driving control. So it's relevant to this workshop. Let me say a little more. One thing that people realize very quickly is that if you use these softmax values as class probabilities, it gives an overconfident result, say on the test set. And what I've plotted over here is exactly what happens when you show a benchmark on a perturbed test set. And what you get, just to emphasize it, is these blue bars are the predicted probabilities, and they're always above the actual probabilities. So if right here I'm saying I'm 85% correct for this bin of images, in fact, I'm only 65% correct. So they're overconfident. And when we're looking just at the test set, we made a proposal to fix this just using some statistical binning ideas. Just convert these probabilities into other numbers, the softmax ones into calibrated probabilities. And I presented it this summer, great. But when I looked at what people really cared about in the workshop is out of distribution, whether it's corrupted data or just not what the model was trained on. In fact, on data it's never seen in training. And this is the workshop down here. So again, this seems kind of impossible. Why should I think that I can predict when I'm going to make an error or not on data that I've never seen, that my network has not been trained on? It does seem kind of impossible, but let's see what people can do. So they take a corrupted version of ImageNet, and down here you see a bunch of corruptions. There's noise added, there's blurring, contrast, brightness. when you corrupt images like this, typically baseline models do very poorly. So not only do they classify poorly, their estimates of whether they're making a mistake also breaks down. Now, there are some very good contributions like a paper such as OGMIX that tries to enhance a network with corrupted data, but different from the data it's going to see. And they show that actually you do better on unseen corruptions as well. So this helps, but there's inevitable trade-offs. If you train a model like this, you see the robustness, accuracy trade-off. It'll do worse on the clean or the training data, test data, than it would have before. So how do we get around this? There's an inevitable trade-off. If I design a model to do better on highly corrupted data, it'll do worse on clean data. And some people believe that you can't avoid this trade-off. Well, one thing you can imagine would be a very complex workflow where you have a detector, and there's been work on detection that detects how bad the corruption is. And then it deploys one of several models, each which are tuned to work best with that particular level of corruption. Then those models would be as accurate as possible and have good uncertainty estimates. But nobody's done this. I certainly couldn't do this. It's just too complicated to have all these models and to train them and to make it work. Maybe something like that could be done in the future. Well, it turns out what we found is that you can get the benefits of this kind of complicated workflow essentially for free. So we take a simple enhancement of our basic in-distribution calibration, which is simple. And doing so, we can beat the benchmarks on this corrupted data set pretty widely across different methods and different intensity levels, all with this one simple add-on. There's no model retraining. In fact, we did everything just by using published model Pmax values. And you just add a little lookup table based on a statistical method I'll describe. So first, the overconfidence. Let me return to this. Well, they're overconfident on the test data, and they're even more overconfident when they're making mistakes. So the way we measure overconfidence, this is the established method, is calibration error. So we make these bins. You could imagine a human being binning problems into problems of different difficulties. And then you count the errors in the bins compared to the predictions in the bins. That's called when you add them up, it's the expected calibration error. There's other scoring methods, such as the Brier score, that are also used, but typically, and we show, it gives almost the same ranking of methods. So what do we not have here? We're not talking right now, although I'll talk later, about adversarial attacks. These are images that are designed to fool networks, and they can cause a network to have very high confidence for completely different images. And there you go. This is just a little joke, overconfidence. It happens with people too. In fact, people often think they know more than they actually do if you ask them to estimate it, but that's unrelated. Okay, so here's the issue. Here's the problem now. That was sort of a story going into the talk. Now, what's the problem we're trying to solve? Increasingly, our models are being asked to perform on data sets different from the training data sets, and we call this out of distribution data. Neural networks do poorly, not as well as expected on OOD data. And one of the cited papers was in a medical setting using neural networks to do classification. And they found, it's highlighted here, they don't generalize as well as previously believed. Okay, so this is a motivation for wanting to have uncertainty estimates so that at least if you're making mistakes, you're aware of it. So let me just show, this is calibration error. It's good to visualize it a little bit. You just, again, bin the images, and in the bins, you look at the predicted number of errors you're going to make and the actual ones. And those are the two colors. So on the left here, the CFAR model has accuracy 94%, and it's making accurate predictions of each of these bins. In fact, the really confident ones are like 99.9%. And the worst ones are something like 85%. And already this illustrates a little bit of the problem. So this is all my data. If I show it a data set where my accuracy drops a lot below 94%, I'm still going to probably predict this average accuracy or a little less, which is why they're overconfident. On the other hand, again, this is on test data. Here's a poorly calibrated model on the right, where the predictions just don't line up. They don't line up with the actual error rates. So you could have a model that's accurate and poorly calibrated, and vice versa. Okay, so now there's a list of benchmark methods. There's a benchmark paper that came out. I'll jump ahead to that. So there's this benchmark data set that these authors here, Ovadia, all the way down to Snowick, they built this data set and they published using a whole bunch of different methods for uncertainty over a whole bunch of different corruptions, the errors, the calibration errors, for example, of all these methods. And so it's a little hard at first to read this plot, and I'm not going to expect you to dive in. But what you see is it's going test, different intensities. Now for each level of intensity, the color represents one of the many benchmark methods. And the whisker plot says over, I think it was 16 types of corruptions, what's the mean error and what's, the quartiles, the quartiles of the error across the different corruptions. Okay, so it's a huge data set. When I got my student working on it, he had problems just downloading it because it was, 40 gigabytes or something. But it's a real resource because previous to this, to try to do benchmarking meant you had to reproduce results, which is very hard to do. So what are some of these methods? Actually, I'll be honest with you, the first 4 are pretty simple to explain. So the vanilla one just takes Pmax, or the labels, the class probabilities as probabilities. Temperature scaling is a method, this is from 2017, that basically just tweaks one parameter in your model to try and get better calibration. It's post hoc calibration, so it's a little bit like what we do with binning, but instead of binning, you just tune the temperature in your softmax, change it from one to something else. Dropout I described before, you wiggle your parameters and you average the p-values. Ensembles, it's a similar idea, but you just have 5 different models, I think, not 10, it says 10 there on. You have 5 different models, you do an evaluation and you average their results. And then these last methods, I'll confess, I don't know what they are. We just implemented them, where we just took their values and compared. But there's some Bayesian interpretation, but they don't perform as well anyways, so it's fine. Okay, so that's the benchmarks. Here's a picture of how our method does do better. So this is one of the benchmarks. This is one of these dots in one of these colored slides, a particular one. It shows quite a big calibration error. And then when we have actually 2 methods, which I'll describe later, but one is you're only given a single image drawn from the distribution. And so you have to calibrate you have to guess based on that. And the other is you have multiple images so you can better calibrate. Okay, so we have better calibration error. That's what you want. And it's a simple method. But let me just say something, thinking about this, right? You shouldn't need to work too hard to improve a model that's always overconfident, right? Because if it's always overconfident, all I have to do is shift all these values by their mean to drop it down so the error is mean 0, and I'll be better calibrated. Of course, the challenge of that is you don't know your error rates. It's unseen data, so you don't know if you're making a mistake or not. If you knew that, you wouldn't even need these numbers. At the same time, if we only need to change one parameter, there should be an intelligent way to do that and get these better results. So really the contribution here is, rather than use a machine learning solution, which is to train a model to figure it out, we just did the statistics. Okay, so here's our results now. It's, I'm going to jump ahead. It's this plot here, simplified to not have the whiskers, just to show the mean. And so across 1, 2, 3, 4, of the 6 methods, the blue curve is the benchmarks, and the orange and green are our 2 methods, and it's a good drop in calibration error. And I have a comment here. The best method is actually the ensemble method, and our improvement isn't as much as we would like it to be. It still improves, but we have a sort of an excuse and apology for this. which is we didn't have all the data. The benchmark data set only gave us the average of the 5 models on ImageNet. If we'd had all 5 model values, I think we could have calibrated better. And that's because averaging doesn't commute with calibration. Okay, so just the more detailed plot. The reason for showing this is that the lower plot is the plot from the paper, and we're able to reproduce it. Or sorry, the higher one is from the paper, and then the other methods are compared with just a hash. So now let me describe the method. So here's the idea, and let me just start with this plot on the right, looking at the blue. So a model calibrated on clean data has a whole lot of values near 1, because it's already 94% accurate. If you're showing it data where it's making a lot of mistakes, these p-values, we just looked at p-max, they shift. Okay, so data set shift is incredibly complicated, not something we could model very easily. But model output shift is very simple. It's just these p-values have been shifted. So we are going to use as a surrogate for data set shift, p-max shift, and just see if that information is enough to calibrate our model. And it turns out that it is. So what we did, instead of just having one model, was we pulled out one of these corruptions. It was the intensity one, contrast, and we measured the distribution of probabilities of the model that we were studying on that. Then we found how much these values were shifted, which is great. Then we calibrated for each of those intensities. Now, when you give me one image, I try to guess based on the p-max value, which level of corruption it's likely to have. And then I use that as a calibration set. And it turns out that's enough to give a huge improvement. If furthermore, you give me 5 or 10 or lots of images, then I can look at the distribution of the p-max values and even do a better fit and get the right shift. Okay, so that's it for this result. I don't think I'll use the time I have now to give more of the details, but I can if there's time at the end or if people have questions. So I've just described it, but I have the formulas if you like. Okay, let me go to the next topic. Are there any questions? Maybe I'll take a break anyways. Were there any questions or comments about this? Because I'm going to next speak about different stuff.
I don't see any questions in the chat, nor do I see any hands being raised.
Any friends want to say hi? Stan, are you there? Stan? Maybe not.
Okay,
right.
So we do have one question. Okay. This method can be applied to any other data set, not just images, correct?
Yes, correct. Yep.
Another question is, how does the method extend to object detection?
Yeah, I guess that would be the question of interest here. It would extend in the exact same way. I think if there's now you're just asking for the probability of an object and the classification. Is there an object there or not? That's 0, 1, but you can still shift the probabilities based on p-max shift. So I think it would work.
Thank you.
All right, great. So let me now go to a different topic. This one's a little more mathematical. It's that neural networks are vulnerable to adversarial attacks. That's a perturbation of an image designed to be small but cause misclassification. So one direction is to empirically train a model, expose it to attacked images to make it more robust. But of course, you lose accuracy when you do that. But the other approach is interesting because it's a certification approach. It's to give a guarantee that a model can't be perturbed for data which are within a certain norm. So if you perturb within a certain size, then I will guarantee that it hasn't been attacked. There's some trade-offs with these models. First off, they're stochastic. The ones that are available now require that you make multiple evaluations of a model, add noise each time, and then average them. And also these models need to be trained from scratch. And so the work I'll describe now is to reduce this trade-off, to give a certified model that doesn't cost as much. So here's an example of adversarial attacks. I think by now many people have seen this. It's these two images look exactly the same to the naked eye, but there's tiny imperceptible amount of noise with this sort of random looking pattern has been added. And it causes the model to go from a panda classification at a p-value of 57 to gibbon with 99% confidence. Similarly, there's real life attacks where you do something to a road sign that shouldn't matter, but causes a misclassification, which could be dangerous in practice. So Alexander Madry essentially promoted an idea that was in Goodfellow, which is to train a model by exposing it to attacked images. And there's a trade-off, a loss of accuracy for more robustness. So when you start to study the robustness of models, you see that there's all kinds of different attacks. There's a whole zoo of them. And you have these kind of survival curves, which is a threshold of how much of an attack you can survive without misclassification. And now it's quite easy to implement these attacks and test a model. But certified methods are doing something quite different. Certified method is trying to say that the model I have is guaranteed to have the same classification for all perturbations eta up to some r, where r depends on x. So how is that possible? The proposal in Cohen, which was expanded on in Solomon last year, is to define a smooth model, which is the expected Gaussian average of some baseline model at a given x. So what does that mean? The smooth model, in practice, you don't train a new model to do this. What you do is you take 30 images, 30 copies of your image, add noise 30 times, measure the labels, and average them. Now, why should this work? They have a probabilistic proof that if I perturb the data and enough, so the certification process, I think I'll get to that in the next slide, but this illustration sort of shows the idea that you are going to smooth the classification boundary. Okay, so you certify by sampling the base model maybe 1,000 times, or more actually, might be more like 10,000 times. Inference requires 30 evaluations. So you're going to lose accuracy on a baseline model when you add noise, so you need to train a model from scratch to be resilient to this noise. Instead, what we're going to do is train a model itself to be smooth. So here's the idea of our model. What we want is to train a model to be the Gaussian convolution of a base model. And what we do is we propose a loss, which when you train a model with this loss, would give you the Gaussian convolution of the original one. And it was known to this community decades ago that adding noise to a model, here at least formally, is equivalent to training with a loss with a gradient regularization. So when Bishop talked about this, what he was trying to do was get a model which was regularized by adding noise to the images. What we're doing is the opposite. We're trying to get a smooth model by doing gradient regularization. Now, in practice, we don't use exactly this loss, but it's very similar. We take the original model, f of x, and we train a model f smooth by adding gradient regularization and just putting a softmax on top of that, which just makes things work a little more efficiently. Okay, so there's a different theorem that basically says if you know PDs that Gaussian convolution is like solving the heat equation, or you can take averages of particles with Gaussian noise added. Okay, so what are our results now? Something that's faster to train and faster to evaluate, as well as certified. So our deterministic smoothing method, so one good thing about it is you only need to train an existing model, so a pre-trained model that's accurate for one epoch. So it's a lot faster to train instead of say 30 epochs, which matters on something like ImageNet. You do evaluation just in one forward pass and it's still certified. The stochastic ones don't have those first two properties. and adversarial training is not certified, also takes a long time to train. So the nice thing about this is you can put this layer on top of any of the models above. And then if you look at inference time, it's much, much faster, especially on CPUs, which nowadays people care about, as well as GPUs. Moreover, the main thing, the certification plots for our model, which is the red one, it does better. It has a larger certified radius compared to the Cohen and the Solomon, which are the only other available models. In addition, if you take like a Madry model, download a Madry model, retrain it for one epoch, you get much larger certified bounds than the original model, about 4 times if you look at this table. Okay, again, I'm gonna take a break. Is it 30 minutes? I have another 10 minutes. I'll explain the details a little bit, but also take questions if there's questions.
There was a question, how do you evaluate the Laplacian of f by introducing noise in the descent equation? Actually, he took his question back.
Oh,
yeah.
Okay. Well, I might have answered that. It was probably good to mention anyways. So our loss, going back to our loss, it's the gradient of the model. So you have the full model, it has tens of thousands of components, and you want the gradient, as each component needs a gradient, then you're going to take its norm. So that sounds prohibitively expensive to measure and train with. And you definitely don't want to do it with the double back propagation, which was the original motivation of that theorem. But the cool thing is we can do it for a low cost. And I think I explained it here. So the issue is this term. How do you train with this term? Well, it's too expensive to do it sort of the obvious way. But we use concentration to measure what do? We do a finite difference. So we detach the gradient from the computational thing. And then instead of measuring the full gradient, we take random projections, which from the Johnson-Lindenstrauss lemma will essentially approximate the true value in high dimensions. And I think we only take one random projection. So it's a very extreme use of the Johnson-Lindenstrauss lemma. Probably we should take 10 or 30 or something like that, but it's very efficient. Okay, and so that's the way we do it. Briefly.
Thank you.
Okay. Let me keep going with the talk.
We had one more question.
Okay.
What if X does not come a priori with a structure that induces natural derivatives?
Say again?
What if X does not come a priori with a structure that induces natural derivatives?
Oh, okay. No, we only do this on images. X has to be in a vector space. If it's a graph or something, I'm not saying anything about that, if that's what the question meant.
Yes, thank you.
Okay. Although I'd love to study neural networks on graphs. Okay, so what is it now? Okay, so this is sort of the theme. Let me just remind you what the theme of this talk is. We're looking in our research group, we're looking for areas where we can throw some math in and make some contribution to deep neural networks. It's pretty hard to compete with the big labs and companies. So we found another area. So neural ODEs appeal to a lot of people because they have some strong math connections. So essentially they're being used. Okay, so let me just mention this is primarily work of my postdoc, Chris Finley, who he's left and now he's a researcher at Deep Render using actually these ideas to do rendering, as well as Levon Nerbekian, who's now postdoc with Stan at UCLA. And Jorn Jacobsen, he was at the Vector Institute at the time, and now he's a senior research scientist at Apple. Okay, so some of you may have heard of generative models and neural ODEs. So generative models, let's see what I've got here. So Goodfellow, brilliant guy, came up with a way to generate fake images using neural networks. So sampling from a distribution, generating new samples. Very cool, very realistic looking. One of the downsides, though, is that you don't know if you're covering the full distribution. Neural ODEs is another approach. It's honestly not as efficient as GANs, but it has this very appealing mathematical structure that people hope to exploit and some other advantages as well. One advantage of it is that GANs can suffer from mode collapse. They could just be memorizing your images. There's nothing to guarantee that they're not, although people have made some efforts there, including Wasserstein GANs, but there's still no guarantees. One way of ensuring that you cover your whole distribution is to use an invertible network. Instead of mapping noise to images and having an adversary or a critic, instead what you do is you map images to noise to train, and then you invert the model. So you invert the function to go from noise to images. This idea came actually from Esteban Tabak, a fluids guy at Quran Institute, very nice guy. And it was sort of converted into neural ODEs by David Duvenode and also by Haber and Rithotto, who are mathematicians. And sort of the most recent thing in 2019 was Fjord, which was neural ODEs for generative modeling. And here's kind of a picture of the idea of the neural ODEs is that a ResNet is interpreted as the discretization of an ODE. So why not just make your model an actual ODE? And instead of doing backprop, you do kind of an ODE solve. Okay, now, sorry, I've been teaching on Zoom for a while, so I'm getting a little tired, but let's keep going. Here's some of the formulas for neural ODEs. The idea is to map one distribution by another. We're mapping to a Gaussian, and our loss involves a log likelihood. So that's the problem. It just so happens that our mapping is generated by not a parameterized function, but the solution of an ODE, which itself has parameters. So what was missing? So we like the idea of using an ODE for architecture. One thing it does is it makes the depth of the network adaptive. The ODE decides if it needs 3 layers or 30 layers. But the problem was there was no penalty for this velocity field. You could have, if you want to get from A to B, you'd love to go there in a straight line because that's more efficient, but you could be wiggling as much as you want. So what Chris and I talked about doing was to just regularize these paths by introducing a penalty for velocities, which wasn't there before. In particular, we want to penalize large Lipschitz constants. Okay. And anyways, there is this problem of lack of uniqueness. There's lots of ways to get the ODE from A to B. So that's what we did. We added this velocity penalty. It's a natural term. And again, we used a similar trick to what we did, I mentioned in the previous thing, where you have, we also put in a gradient of velocity penalty as well. And we use these finite difference tricks for that. So the idea, let me just flip back, is previously you might have had a wobbly solution like this, but with this penalty, it's going to try and give you these straight line paths. And there is a connection that we sort of explain a little bit in the paper, that when you add this penalty, you're essentially getting the Lagrangian formulation of the Bennett-Mubrane formulation of optimal transportation. Okay, so replacing integrals by sum, so it's empirical, and the push forward condition that's strict here by the log likelihood, which is a soft version of it, we get our loss, which we can interpret as the optimal mapping in terms of the L2 transportation cost from one measure to another. Okay, well, that's all beautiful math, but there's plenty of beautiful math ideas that don't do anything. And the nice thing about this was it worked pretty much from the start. When you put in this penalty, the model's trained a lot faster. And one of the issues with these models is that they do train slowly. It's an adaptive ODE solver. But again, you're not putting a constraint on the velocities, so it could require a lot of steps. By putting in the regularization, the model ODE could solve more efficiently and the training went faster. That was the main contribution. Generated images. Generated images, they don't look as good, which is fine. And that's it. Thanks a lot.